Excellent. So, welcome to class. We have several things to go over today. First off, I would like to ask how are things going with the science project, with the astronomy project? Any questions, comments? I haven't seen any team posting anything, but I've seen some messages going about having some troubles getting together with the team and stuff. So that is part of what we are trying to do, is to learn how this works. Okay, so go ahead. Okay, go ahead if you have a comment or questions about the project. This is the time.
I actually have a question.
Go ahead.
Is there anything specific that you want?
Okay. Yes, there is something very specific that I want, okay? And what I want is for you all to learn and to, through the project, demonstrate your learning, okay? And to develop, kind of a discipline of investigating topics, asking questions, all right? And one to the working. I also want to see how this working together as a project works for you. Okay, does that answer your question, Emma?
Yes, it does. Thank you.
Can you see that I'm careful not to tell you exactly what I want as far as the project goes? Okay, because that is part of what I'm expecting you to figure out, to learn, and so on. Again, this is what is called an ill-defined problem. All right, it's different than a school where you usually get an assignment that is either a multiple choice or something that is very specific that you need to accomplish. Okay, here this is actually more real to life, where problems are basically very open-ended, and sometimes you have to figure out what are the actual objectives. So the first part of the project is to figure out that. Okay, Rodney asked the question in the chat, did you want us to design a probe? Not yet. So that will come later at other stages of the project. Okay?
So you do not want us to design it?
Not at this point. All right. So for this assignment, let's go back to the assignment. Let's see if we can see that on the screen. Let me try to show that really quick. Okay, here it's coming. So it says, start working on a group project to send a probe to explore asteroids. Define the goals for your mission. What would you like to explore and why? How would you do it? Okay. Brainstorm on the systems needed to accomplish the mission. At this point, this is not a detailed design or anything like that, but basically you would need something, to launch the probe, to communications, the things that we would talk about last week, all right? But this is basically the definition of the mission. Rodney, did you have a question?
Yes.
Go ahead.
Do you hear me?
Yes.
So we're on lesson 17, not lesson 18, right?
That's right. Yes.
Okay. I was like looking at both of them going, okay, I have to include all of this in one. And I thought today was the day we're supposed to turn in our report.
For 17.
For 17.
For 17.
Since I thought we were doing them together, it's not really, I'm sorry.
Okay, no problem, no problem. Okay, so do you understand that we'll be basically working on this project in several stages? Okay, this is kind of like the rocket. All right. So the first part of the project is basically just the definition of the mission. So it's lesson 17 is to start, defining the mission, the objectives, the goals, okay, and then what is it that you are going to do, why, that type of thing, very general, okay?
I got with my team and we were talking specific stuff, like all week long. We're like, we don't know what we're going to do this. This is like a lot. We need like a week more to do this.
Of course, yes, and you'll have several weeks, okay? So the detailed design of things, we are going to do those in small pieces, all right, and they will be different parts of assignments in different lessons. Is that okay? All right.
Yeah.
So, but
okay.
Is that clear to everyone? And it is a group essay, so you can submit this as a group. All right. So Haley asked, it's a group essay, correct? Yes, it is something that you turn in together as a group. All right. Any other questions on the assignment? Go ahead.
We can turn it in as a group essay. Does that mean I can write a part, Annika writes a part, Nathan writes a part?
Yep. Okay, and so you write different parts and then you put them all together and submit them together as a group. Okay, so that is why I suggest, one of my suggestions would be you could write it in a Google document, so you can all edit that same document together at the same time. Okay, you can say, all right, Nathan, you write this part of the report. Rodney, you write this other part. Okay. Annika, of course, is giving the directions here. and she writes some other portion of the project, and then you submit it all together. Okay. Is that all right?
Yes. Especially now that we know we're not doing 17 and 18 together.
No. So, yeah, so you do them separate, okay, and so concentrate, read the assignments carefully, all right? So can you see that this says write an initial 2 to 3 page group report for your proposed space mission?
Yeah.
Wow.
And the next one says 3 to 4, and I'm like, whoa, the numbers are changing. This is weird.
All right. So, excellent. Good deal.
You guys are supposed to catch me when I start making assumptions like that.
Yes. Have you had trouble getting together as a team? What has been the thing that works best for you?
GoToMeeting. I use GoToMeeting. I went on and hosted my own GoToMeeting.
Excellent.
Together, we talk. Boom.
That's right. Yeah. So you can use GoToMeeting. It's you just do it for free. Okay.
Yeah.
And so that is a very good way to do it. Okay. All right. Okay, Sabrina, I'm glad that makes sense. Elizabeth, 14. I don't know what 14 means, but 14, good. We are okay. All right. So we have that. Let's put that to rest for now. Keep working on this and just submit the lesson 17 project. Okay, wow, Sabrina and siblings, multitude of siblings there. It's awesome to see you all. Woohoo! Good deal. All right, I'm going to minimize the webcam here, but you can still see me and see each other. All right. So today, actually, we are going to switch gears. Okay. And we are going to start the unit on geology. And so I went basically first to Wikipedia here and to the article there on geology, and I start looking at the different things on the article. This is a very, very interesting. All right, excellent. So it looks very interesting, you know, all the different things that are here in geology. You know, the different topics, time scale of geology, the principles. This is a very, very interesting part that I would like you to study carefully. What are the principles of geology as a discipline? For example, the principle of uniformitarianism, something like that, I guess. All right. So basically, this is a principle that states that geological processes observed in operation, all right, at the present time have worked in much the same way over geologic time. So this is a very important principle of geology and of science, okay? But basically, the things that work in this time also have worked the same in the past. So, for example, gravity. We see how gravity works now. We can see the effects of gravity. We can assume that gravity has been a universal law in effect all throughout the history of the universe. Okay, so these are very, very interesting principles that help you to understand how geologists actually are able to study geological features. Okay, so here we have, you know, geological materials, okay, this rock cycle, in an introduction to plate tectonics and the earth structure. Today that is the topic that we are going to go into more detail and so on. But this is a fabulous article, and it has, of course, tons of little links to other articles that you should venture into and go to read. I love this section here on applied geology that talks about what are the different disciplines really on geology. Okay, I really like hydrology or hydrogeology, that is basically the study of how water runs, and groundwater and underground water, how does it go and where it's found. So when I was young, okay, I think that I started this around when I was 8 years, 9 years old. My grandmother had a set of an encyclopedia that was very interesting. It was 13 volumes. Each volume was about this thick, okay, on the encyclopedia, and they were books about this tall, you know, and this big. And it wasn't an encyclopedia order in alphabetical order, okay? You know how most encyclopedias have basically entries about words, and they are all in alphabetical order. This was a thematic encyclopedia. So it was, each volume had a theme or several themes, okay, and it went in depth into that theme. For example, one of the volumes was on geology, another one was on biology, there was a volume on astronomy, and so on. And I remember that one of my favorite things to do was to grab those volumes on the encyclopedia and just read them. Okay, I would just get the topic, that I was interested, like geology, and I would start reading and reading the whole thing. It was really, really interesting. One time I spent a whole summer studying a whole volume, the one on geology and biology, and I tell you, I still remember exactly, okay, the things that I read in those volumes. And so nowadays, we have actually even a greater blessing, really, with the internet and this idea of Wikipedia. We have really a thematic encyclopedia of everything that you would want to know at your fingertips, and it's really available. And you can go as deep as you would want to go by following the links and everything. Rodney asks, you must have had plenty of time, eh? Well, I was about 10 years old, and during a summer vacation, I didn't have a whole lot to do, so I just read. That was my favorite thing to do. I read a lot of Jules Verne books, and I read this encyclopedia, several volumes of this encyclopedia. To me, it was fascinating, really. So during the school year, I have to tell you, I almost never had to study, okay, because I still remember the things that I had read in the encyclopedia, and so I could talk, for hours, okay, on stuff, pretty much like I'm doing now. So no, there were no computers at that time. Computers were, there were only the big, huge computers, and no computer games to waste time onto. So my invitation really to you is that in the lessons, okay, for example, if we go to lesson 19, that is the lesson for today, I'm going to put, and I have done this also in the past in the other lessons, I put just a few links to some of the resources that we use here, okay, like for example, the geology article and the structure of the earth article. But that is kind of an invitation for you to just begin studying, all right? What I would love is for you, as you read the article, to keep clicking. If you don't know something, all right, okay, and you want to know a little more, just click on the link and go deeper into that, all right? So today we are going to talk about the structure of the earth. And I have a presentation here, and I use 3 images actually here from this article in Wikipedia. And so I'm going to go to that. All right, let's see here. And so we are going to start with looking at the different layers of the earth. Okay, you probably have already looked at this in other lessons, okay, or in elementary school. You may have already done some of these. What I would like to invite you to do is to study these layers of the earth deeper. Okay, so here we are at a high school level class. So, and it is really for you to study these things. And so study them a little deeper. So we have, if we go from the inside to the outside, we have the inner core that is solid, okay, and extremely hot, all right? So the inner core of the earth is probably as hot as the surface of the sun, not the inside part of the sun. Remember when we were doing the sun lesson that the core of the sun is a lot hotter than the surface of the sun, but the surface of the sun is actually hot enough. It's not a pleasant place to be, really. All right. Then you have the outer core that is also liquid. All these, the core and the outer core, the inner core and the outer core, are both metallic here on the earth. So They are made actually of iron, nickel, and some people also think now that some other metals like or gold and other precious metals are also part of this inner core. The question that I have for you is, why is the outer core liquid and the inner core solid?
To protect the Earth. If the outer core was softer, then maybe when stuff came to hit it, it could damage stuff. But since the outer part is harder, it has more protection.
Okay, well, yeah, that would be a kind of a practical answer to the question. Okay, certainly you don't want to have anything that hot, okay, on the outside where anybody can touch it, okay. And so it's a great thing, really, that the core is inside, all right, like Nathan is saying. But let's see, Annika, you say pressure, and Ashlyn says because, all right, because it is so dense and under so much pressure, the density is higher. Let's see, Sabrina, the inner core is solid because of the pressure of the outer layers. The outer core is probably liquid because of the heat from the inner core. Okay. Dallin, it was discovered by looking at seismic waves generated by earthquakes. Excellent. That is a great point, okay, of how this knowledge is actually known. It is really by looking at how seismic waves propagate through the earth, all right? To promote motion, the plates on the earth does move and it needs to, okay, so that would be also a practical reason for that. But the actual reason is exactly what I think here Annika, Ashlyn, Rodney, and Sabrina are saying, is that the reason why it is so hot and why it is liquid and solid is because of pressure. Okay? So we haven't, someone was making a comment here about drilling a hole on the earth, and we have not been able to get even to the mantle, all right? In fact, we haven't even been able to get to the crust of the earth, okay, drilling holes. So it is not a very easy thing to do. So there is really so much pressure. But the interesting thing is really that as you go deep, all right, the temperature rises because of the pressure of things that are the weight really of the material that is on top. The gravity pulls that down, okay? And so when things get pressurized, they heat up. I would like you to do a little experiment about that. Do you have at home kind of like a syringe? You know, one of those syringes that you use maybe to give medicine or something like that. So if you open the syringe and let it be filled with air, okay, and then you hold the tip of the syringe. Let me see, I'm going to put the, okay, cancel that. I'm going to put the webcam here. So you have the syringe, you pull it out and fill it up with air, and then you block the tip of the syringe, and then you push, okay? You push that air, so you basically apply pressure to the air inside the syringe, okay? Air, because it's a gas, compresses, so you are going to actually be able to push that quite a bit because it's just a gas, All right. What happens if you really put a lot of pressure there? What happens as you put pressure onto the syringe? Yeah, your finger is going to start hurting, okay? Because it's going to feel all that pressure right there on the tip of the finger, okay? What else are you going to see inside the syringe, or if you touch the syringe out? What are you going to feel?
Probably heat.
Heat, that's right. Yeah, the temperature is going to rise, okay? Yes?
I'd like to give another example. This one's really, I do it all the time. Is take a piece of metal and I hammer it on the anvil, cold piece of metal, and it just moves it a little bit. By the time you're done hitting it a couple times, it is now scalding hot. Or you're using a hacksaw.
Yes.
You're sawing and you touch it, you're like, ow, that's hot.
That's right, yeah. So the friction, the movement, okay, the pressure of the hammer, anything, all those things basically add pressure and heat things up, okay? Also, you can try, if you have a bicycle, especially if it's a racing bike, okay, that has a very skinny tire that holds a lot of pressure. When you inflate the tire, okay, how many pounds of pressure does a tire hold?
30 pounds of pressure per square inch or more.
So a car tire is about 30 to 35 pounds of pressure per square inch, okay? So the bigger the tire, the lower the pressure, all right? A bicycle tire, just a regular bicycle tire, would be about 40 to 50 psi, okay? A racing bicycle that has a very small tire, very skinny, you have to inflate those to about 100 to 120 psi. Okay? Yeah. If you are actually an indoor racing bicycle, those that are going for speed records and so on, they are at about 190 psi. Okay? Yes, and the interesting thing is that as you push the pump, all right, is it going to be very hard to push 190 psi? Yeah, it gets really, really hard. If you touch the tube that goes into the tire, it's going to be freaking hot. Okay, it's going to be burning, really. So you have to be careful. Because again, the air, and this is just air, that you pressurize is going to raise the temperature. Okay? So imagine here what happens to rock as you put a mountain of rock on top.
Turns to lava.
That's right. That is exactly why the temperature rises, is because of all that pressure. All the material that is on top of something, okay, is going to add to the pressure of that something underneath. And it's going to make it smaller and smaller, compress it and pressurize it, and it's going to actually increase in density and it's going to increase in temperature. Okay? So that is why the mantle of the Earth is let's see here. Let me go here back to the presentation. Okay, let's see. Okay, so the mantle of the Earth is stiffer, but it's still not liquid, but it's plastic. It moves. All right, and that is what causes the plates, to move and so on. All right, and then the inner core is liquid. Okay, so the lower you go into the Earth, the higher the temperature, and then things get denser and denser, and they actually start changing state, okay, as they get hotter. All right. Yes, Sabrina says that coal with pressure, under pressure, turns into diamonds. That's absolutely right. Okay. In fact, you can actually make artificial diamonds by doing that. All right. Let's see if I can go here in Wikipedia. Let's go here.
My dad does that for work. He
Oh,
makes artificial diamonds.
is that right? Okay, tell me about it. Where does he work? How do they do that?
No, he works at Novatech,
Uh-huh.
and they have these presses.
Yep.
And the presses that David Hall designed, probably with Dad. He's like one of the top managers. It's a cube. And then they have these giant presses, these giant hydraulic presses that come in at all these different angles. And they all meet at the center to put pressure on a kind of like a silicone cube itself.
Mm-hmm.
And inside that cube, there's like graphite, or whatever powdered diamond they want.
It's coal, okay. Mm-hmm. It's carbon, basically.
Carbon. And then they apply pressure.
Mm-hmm.
And each one of those anvils or presses gives about 50 million psi.
Okay, so here we have the article on that, and here you can see basically what Ron is talking about and how these anvils and the dies are basically all meeting together and applying pressure there to this little piece of graphite, which is carbon, and then as the more pressure, it turns actually into a diamond. Okay? Why do they do that, Rodney?
What?
Why do they do diamonds?
When do they do diamonds?
Or no, why do they do diamonds? Why do they create diamonds? Mm-hmm.
The ones we're working on, my dad's working on, or has been working on, is drilling bits. So
That's right, yeah.
They would put diamond bit heads. I'm trying to find one, but couldn't find one yet. Is they put them on drills so you could help drill for oil.
Yeah.
And one of their latest things they did is, those big machines that mill up the road, asphalt and stuff like that. There's these picks, right?
Mm-hmm.
Well, usually you have tungsten carbide, and they last about 24 hours. And then you have to stop. You have to hammer them out, pound them out. Costs money to replace it, to stop the whole thing, to replace them. They took that and they made it bigger. They put a diamond head on it. It now lasts 2 weeks, about 2 weeks. A lot longer. That was one of the things he's working on.
Mm-hmm.
I'd like to go get something if you'd like me to show him what it is. But it'd take me a little while, just like a minute.
Okay, so there are some questions here on the chat. Is what type of metal do they use to press it? So the press itself is probably made out of steel. Okay.
Yeah.
And how long does it take to actually do the pressing?
I don't know. I've never run a press, but I know if they fail, something flips. It's a humongous, ginormous sound.
Yeah, because imagine if for some reason one of these dies or anvils do not resist the pressure at the same pressure point of the other ones, it is basically like an explosion. Okay, all right. So imagine here we are talking like when a bicycle tire explodes, you hear it, and it makes a big explosion. That is just 120 psi. Here we are talking about 15 million psi.
Per press, and there's 6 of them.
That's right, yes. Yeah, absolutely.
One of the biggest things that I actually helped a little bit with the process. One of the things they do is they have like this little foam square. They put it underneath the silicone cube that just kind of helps hold it in. So the silicone fall out and it goes. So I used to make those pieces, and I used to make thousands of them, hundreds of them.
Wow.
So a lot of times, what happens is they reuse that piece, and it'd fall out. It'd be an explosion or a loud noise. Like one guy that wasn't paying attention. So.
Yeah. So here we have another diagram here showing, the steel outer anvil and then a tungsten carbide inner anvil. And then this is the core, the part that is going to be pressurized into a diamond. All right. So how do you think that natural diamonds are formed then? How are natural diamonds formed?
Pressure?
Pressure, that's right. Yeah, it's not chemicals, okay. It's really pressure. Tons of crashing rock. So by being buried under the earth for thousands of years. So the carbon basically is under a whole mountain or several mountains, and the pressure there is basically what turns the carbon into diamonds. Okay, so that is really how it happens. So that is that the artificial process is basically kind of the same type of idea, but it is being done faster artificially, so that is again pressure. So then
Here's some diamonds, if I could.
Oh yeah. Let's see the webcam. Okay, yeah. All right. So do you?
This is more of a flat one, and they've made several shapes, but this is one of them. So it's made to like scrape and cut like that, and it'd have tons of these.
Okay, so the diamonds are very, very small. They are kind of like a little powder, and they are glued to that surface. And because diamonds are so hard, they are the hardest thing really that we could find. They cut anything. Okay, that is why they are used to cut steel or to cut, concrete or pavement, and all those things.
It's really funny. Sometimes they'd have to grind some of these diamonds. So what do they use? They use like diamond grinding wheel.
Yeah.
My dad told me it's like trying to cut down a tree with a wooden axe. That's it. A lot of axes. So there's another shape. It's a cone shape. Closer. So
excellent.
You see, it's a little piece, and it's glued to a piece of tungsten carbide. But that's what they make. Just make these little pieces that are just basically the tip of the spearhead, so it actually goes deeper and lasts longer. That's what my dad works on.
That is so cool. Yeah. And that one says, yeah, they have to use diamonds to cut diamonds. Yeah, that's right. Okay. You always have to have something at least as hard as in order to cut something else. Okay. So very, very interesting. And so here, if we go here back to to the inner core. Now I have a question. So we were talking about how the material, rocks and everything gets hotter, all right, and it gets more liquid, because what are the different states of matter? You have solid, liquid, gas, okay, and plasma. Excellent, yeah. So and of course here, as it gets hotter, it goes from solid and cold on the outer, on the lithosphere, to being hotter, plastic, malleable, and then very hot and liquid. But the question that I have then is, why is the inner core back to solid if it's actually hotter than the outer core? Mm-hmm.
Yeah, just make sure you don't drop it. Diamond is still extremely hard.
Yes.
Mm-hmm. Glass.
Yeah, Annika here makes the comment that you can prove that by trying it. You try the diamond against the glass. If it marks the glass or cuts the glass, it is a diamond. Mm-hmm.
Isn't it true that only a diamond can break a diamond?
Yes. Mm-hmm. Well, yeah. Yeah, so you need something that is at least as hard, okay? Now, there are other ways of cutting diamonds by hitting them, okay, right in the in the break of the crystalline structure, all right? When we get to that part of crystals, there's one lesson on crystals, and we can see that crystals have different structures, and so the way that diamond cutters actually make the cuts on the diamonds is by hitting them in the specific places where the crystal kind of is weaker, it breaks. Mm-hmm. Okay.
Yeah, the only way to cut diamonds is usually with a diamond.
Yeah.
The diamond will break, okay? I said that the bits last for about 2 weeks. The diamond does break against asphalt or concrete. So it wears out.
It wears out, yes. Mm-hmm. It wears out, but it does a lot of work. Okay. All right. So, any ideas of why the inner core is back to solid?
I think it's like still liquid. It's just so pressured together. It probably is a solid.
That is actually the right answer, Rodney. That is correct. Okay. So the reason why it is solid is because of the extreme pressure, the extreme density. Okay. There's so much pressure in this liquid magma. All right, that now the atoms, the molecules of the metal are so close together because of the pressure that they basically behave and turn back into a solid. Okay, but they are very, very hot, and so they should be kind of liquid, but they are solid because of the extreme pressure that they are under. All right, so very, very interesting. And it's actually a great thing because that inner core, this inner core rotating around this liquid outer core, is what makes the Earth's dynamo, which is basically the Earth magnetosphere, the magnetic. Now I'm losing the word. Okay. So, the magnetic poles and everything that are around the Earth are because of this inner core that is metallic spinning inside the Earth. And that generates a magnetic field. Magnetic field, that's the word that I was looking for. Okay. All right. So, let me show you this other graph. This also comes from the Wikipedia article. And in here, the interesting thing to note is there's two dimensions for this graph, to read the graph. So here we have from the center of the Earth. So let me get the pen. So this would be the center of the Earth to the surface of the Earth, about here. All right. So in kilometers, the radius of the Earth from the center to the outside. So there's about 6,000, close to 6,300 kilometers, all right, of the radius. Mm-hmm. And then this other part of the graph shows the density of the material at the different layers of the Earth structure. All right. So what is density? Any idea what density is? Elizabeth said, because Wiki knows everything. Yeah.
Density.
Yeah, what is density?
It's kind of the amount of water. And one second. I was reading this one book. Let me get it. Archimedes and the Door to Science. Have you ever read that book?
Yeah, yes. Mm-hmm.
I'm pretty sure you have. It's really small, but it talks about density and it really explains it pretty simply. The way he figured it out is different elements have different weights. Mm-hmm. How do you tell that weight? So what he did is he took the king's crown, which he was afraid that it was, so the guy put like copper instead of gold, and he put it in a bowl of water and measured how much water was displaced. And if it was gold being heavier than copper, more water should be displaced. You put the same amount of gold in the same amount of water and measure the differences in water. That's probably really long and complicated, but
no, that is right. What was he using the water for?
Displace. He was using the water to measure the displacement of the crown.
Yeah, we call that the volume. Okay. The volume of...
I think it's because...
Yeah.
He could measure the water, but he couldn't measure how much, whatever it was, like, I don't know, the density of it or whatever.
Yeah, so imagine the king gave him like a pound of gold to make him a pure gold crown. Yeah. Well, he came back a pure gold crown weighing 1 pound. Mm-hmm. But what if he copper, which is lighter than gold? You'd have to, how do you compare? I mean, it weighs a pound, see? It's golden. Here's a pound. How do you measure that? So you would see how much water displaced, the volume of copper is different.
That's right, yeah. So I'm going to put that as an assignment here on the lesson, okay? To read that book, okay? Type in the chat the name of the book. Archimedes, all right? Or you can find this story also on the web, but it is really a very interesting story because that was how density was discovered, really. And it's a fabulous story. So density is weight times volume. So how much something weighs, that is kind of easy if you wish to find out. All right, you put things on a scale and you can weight, like in this case, the crown of the king. You can do that, all right, no problem. But the problem is, how do you measure the volume of the crown? Because the crown is very intricate and everything. The volume is the space that something occupies, how much space it occupies, all right? And so the way to do that is by simplifying, and so he used a cylinder of water, okay, and submerged the crown into the cylinder, and the crown displays, basically the water increase in the cylinder the same amount as the volume of the crown, okay? And then it's easy to measure the volume of a cylinder. Archimedes figured out the formula for that, actually, okay? And but it's relatively easy to do that. And so he was able to measure the volume of the crown and find out whether the crown was actually made of gold or if it was less dense. It would have been because some of the gold was replaced with copper or silver or some other lighter metal, okay? So the denser something is, it means that it occupies, by weight, it occupies a smaller space, all right, you have something that is more dense, okay?
I think of like an orange and a roll. You can easily tell the difference in weight, but they're both size.
Yeah, yeah. Or if you have a metal, ball, okay, and a ping pong ball, all right, they have the same volume, but they are, very different in weight. So the metal ball is more dense, okay. That is the book, all right. Beautiful, beautiful book, really. All right. So in this graph, what this graph is showing is showing the density of the Earth material as it goes deeper and deeper into the Earth. And you can see that the Earth crust, okay, is not very dense. Okay, so we have here is kilograms per cubic centimeter. So meter times to the -3 is basically a kilogram per cubic centimeter, and then this times 10 to the third. All right, so it's thousands of kilograms per cubic centimeter. So a centimeter, it's about this much, okay, so it's about this much. So if you have a cube of material, all right, the density would be how many thousands of kilograms would this little cube of material be, okay?
So 3,000 kilograms, or no?
So over here, if it's here in this part of the scale, that would be 3,000 kilograms per cubic centimeter. Okay. Let me see
Times
if no,
10.
I think that this would be a decimeter. Okay, to the -3 would be a decimeter, so it would be a cube of 10 centimeters. Okay, so about this much. All right.
Like that.
Yeah, that's right. Okay. So that is how it goes. So that is what this is showing here in the scale, and so you can see that the Earth crust is relatively very uniform in the density. Okay, it starts increasing in density, but pretty much it goes from nothing, okay, very light density once it goes into the ocean. So by the way, the ocean water, okay, has a density of 1, okay, 1 kilogram. That is actually the definition of the kilogram, is 1 kilogram is a cubic, okay, a cube of pure water of 10 centimeters per side, all right, which is also 1 liter. That is the definition of the liter, all right. So the density of water is 1. Salt water is less dense, that is why it floats. You can float better in salt water because it's less dense. But that would be on the oceans. But now we are talking about the Earth crust, and you can see that the Earth crust is getting more dense. And then there are these areas here where there is a jump in density. These are what is called the discontinuities. So there is a part where the different layers meet, where the density of the material changes all of a sudden, okay? And then you have a pretty uniform set of density for all that part. So this thin layer here, this is the lithosphere. Then you have a discontinuity at this point. It's called the moho layer, and that is because of the name of the guy that discovered it. Okay. It was a much more complicated name to pronounce. It was a Croatian name of the guy, so we just call it the moho discontinuity between the lithosphere and the crust. And so this part here is what is the crust, the density of the crust, and the depth of the crust. So the depth of the crust goes from about right here, okay, all the way to this area. All right. And then you see there's another discontinuity, another jump between the crust and the mantle. Okay. Can you see the change in density here between the crust and the mantle? There. And then the mantle is pretty uniform in density. It increases in density as it goes deeper. And then right about here, okay, at about 3,500 kilometers, we have a huge change in density, a huge discontinuity between the mantle and the core. And then there's another discontinuity of density between the outer core and the inner core. Mm-hmm.
Why does it jump so fast in density instead of gradually? Like, why isn't it go gradually, like just as much as you get gradually more weight on it, the more further down you go, but instead it goes all of a sudden different density?
That is an excellent question, Rodney. Excellent question. And the reason is pretty much the same as, have you ever put in a jar, on a cup, you put water and oil?
Yeah.
What happens when you put water and oil?
The oil floats.
The oil floats. Okay. Why?
Because it's out of a lighter density than water.
That's right. Because it has a high, it's lighter in density. Okay. Well, so if you were to measure in this, let's say that we do this same graph here between water and oil, so you would have the same type of thing where you have the density of oil, okay, the density of oil here, and it would be the same density, all the part of oil, and then there's a huge discontinuity between the water, and then you have the density of water.
So what?
Can you see that the layer, the part there, right there between water and oil, you have a discontinuity.
So really,
it's jump.
Elements change all of a sudden.
Very, very much. They change a lot, okay, in density. So the density of the mantle is a lot different because it's a lot lighter than the density of the core. Okay. So you really can see how this, because of the changes in density, you really see that all the different layers are really floating on each other, floating on top of each other. Isn't that amazing?
Yeah, I was just thinking, like, how did these things become in order so perfectly?
Because of weight.
Because of weight.
The heavier they are, the deeper they go into the earth. They sink.
Do we know what these elements are then?
Yes, of course. Of course. So the core is metallic. Okay. So they are heavy metals, iron, nickel, gold, and all the heavy metals, they sunk down into the core. The mantle is basaltic, okay, so it's more rock, and so you have different, and then the crust is even lighter rock.
And yet we somehow still have a lot of metals on the crust.
Yes, thank goodness we do, because that allows us to do mining and everything. Okay, but I don't know if you remember when we were talking with Dr. Lewis about the asteroids, he was mentioning that one of the things that are important about asteroids is that because they are not very big, they don't have enough gravity to pull the heavier metals inside into the core. And so it's actually easier to mine heavy metals in an asteroid than on the Earth. Because on the Earth, the heavy metals have sunk for the most part.
It's big.
Yeah, yeah. So imagine that how big this is, that all the mining, all the things that we have done, okay, all our activity is just has always been in the lithosphere. We haven't even done anything to get to the crust. Okay.
We haven't even touched the crust.
No, that's right. So there have been some projects to try to get here to the Moho discontinuity, and they have not been able to get that deep.
That's really deep.
Yeah. But imagine this is just this deep, okay? That is this difference in depth, all right? This little part. Okay.
Earth is huge.
This is a huge world. All right. So sadly, our time has gone. Okay, but I think that we have touched on a lot of very, very important things here today. Okay, we've talked about the pressure and how these materials sink and the density. All right. So I want you to look there in Wikipedia. Yeah, time flies when we are having science class. Yes, I tell you really. So keep studying these things. All right, keep reading the articles and everything. The assignment for today in the class. Let me see. Oh no, we don't want to end that. The assignment in the class is let me go to that. So research. Yeah, the assignment for the lesson today is research the composition of the different layers of the Earth. So that is kind of what Rodney was asking. What are these layers made of? That is what I want you to study. Find out what are they made of. And then, a fun thing, compare and contrast the composition of those layers with the geological compositions of another planet like Venus. Okay, wouldn't that be interesting to do? And then to write a 2-page report on your findings. We didn't get to the gospel principle here, so next time we are going to start with that, because this is really a fun thing that I would like to do, especially with this group. Okay, all right. So any questions about the assignment for this lesson? Go ahead, Nathan.
Is it true or false that we only have to do 11 of the assignments in the course to pass?
It is true.
Is it 11 assignments per semester? So this semester I have to do 11 assignments to get credit for this?
What I have heard basically is that is one assignment per unit. Okay, so if we go here to the modules, so this would be 1 unit, another unit, 3 units, 4 units. Okay, this is 1 unit. The lesson 19 is 1 unit in itself. Okay, so I guess that you should do this assignment. All right, then we have unit 6, unit 7, 8. Okay, and then so this one, the final exam. The projects are basically counting as a unit, so you also have to do those, and I give you 150 points. So yes, that is actually true. There have been some students that are very diligent and have turned in a lot more of the assignments. Okay, and that is great. Okay. So yes, Sabrina, we have that is something that I mentioned at the beginning of class. But I put assignments basically out of every lesson for every lesson, and then you can choose which ones to do. If you want to get a school credit for the class, you need to turn in at least these 11 assignments. If you turn
All right.
more in, the more the better. Okay, and of course, this is all about your learning. It's not about my grading. Okay. Does that make sense?
Yeah.
Good deal. Mm-hmm. Yeah, so we have heavy metal comments going on around. All right, let's finish with a word of prayer.
Actually, can I
Yes.
ask one more question?
Of course. Mm-hmm.
So, for the science project, I just want to get this clear. We do not have to worry about the landing part.
Landing back, coming back to Earth, you mean?
Yes.
No, I would actually suggest that you do this as a consumable probe. So we are going to send this probe somewhere, and it is not coming back. Okay.
Sending anyone, Nathan. Goodness.
Yeah, we will say goodbye at some point after it accomplishes its mission, and that's it. So yeah, so yeah, we'll get rid of it.
Are we gonna land it on whenever we send it to? Do we have to like?
If you want to land it, you can plan for landing, okay, or you can plan just to visit areas and so on, like the Dawn probe that we were talking about last class. Remember that it visited Vesta and now is going to meet with Ceres in about a month. All right, so we are going to participate on that, okay, as a class. We'll look that. And so they are not planning on bringing that probe back or landing that probe into the asteroids. They are just flying by, doing a flyby. And the flyby allows them to take pictures, to do analysis of the composition, to really study the speed, the trajectory of the asteroid, and a bunch of things that they wouldn't be able to do from a distance. And so that is the purpose of those probes. So that is kind of similar to what I envision your project doing. Mm-hmm. Okay. Were we supposed to research systems for the probe? Yes, but these are not, you don't need to turn that in at this time. Okay. So that would be for other times. Mm-hmm. Yeah, you can slingshot the probe from a planet or an asteroid, okay, and see how what that does do to the probe. It usually accelerates the speed and everything, and then you send it to somewhere else. Mm-hmm. Yes, Rodney?
Are we going to write this report for lesson 18? Are we going to write it in past tense or in a future tense?
Future tense, yeah. Yeah, you are going to plan to do it. Mm-hmm.
Okay.
Yeah. Okay.
Like this year or like years ahead?
Oh, you can plan it with whatever amount of time you need. Mm-hmm.
It's gonna be next month.
Yeah. Well, imagine these things take time. Okay, even if you were to have already everything built and ready to launch and so on, just to get to an asteroid, let's say that is beyond the orbit of Mars, it takes years. Mm-hmm.
Do we have to plan the trajectory?
I would love if you could do that. Oh, Haley, not 10,000 years. Come on. Or not in the. Okay. All right. Let's finish with a prayer, shall we? Okay. Annika, would you like to, please?
Sure.
All right.
Our dear Heavenly Father, we're grateful for this day and for the opportunity we have to learn about Thy gospel and Thy creations. And we're grateful that we can have connections with people all over the world and be able to learn together. And we love Thee and say this in the name of Jesus Christ. Amen.
Amen. All right. Amen. So let me